Lab 2, Motion of a falling object. Lab summary. Using the fundamental principles of Newton's second law, also referred to as the momentum principle, I observed a falling object's position over time. Alongside that, I observed the motion of said object via computational models that incorporated gravity and drag and gravity respectively. Using observations and my computational models, I answer revolving questions about the forces of gravity and drag. Video summary. I observed the motion of an object in a straight path experiencing forces of both drag and gravity. For the video, it was recorded in 30 frames per second. In time, it was 0.801 seconds. For the environment, it was indoors to reduce the impact of factors outside of drag and gravity. For the system, I used two standard pieces of copy paper, balled into a ball, around 5 grams. End position of the ball was minus 1.885 meters from the origin. Computational model, gravity. I set t equal to 0.801 and set the initial velocity to 0, 0, 0 due to rest. Velocity and position update formulas were derived from Newton's second law and the definition of average velocity respectively. Here you can see the position of the ball over time, and below you can see the code. In the end, the object's final position according to the gravity-only model was minus 3.15 meters, traveling significantly farther than an observational model. Computational model, gravity plus drag. For the program, everything outside of FNet remained the same. FNet. FNet for this model was derived from downward force of gravity plus the upward force of drag. Drag force was determined as b times velocity squared in the upwards motion. B equaled 0.45 as this is what gave me the best results. The object's final position in this model was minus 1.85 meters, almost exactly the same as my observation model. This is my graph. As you can see, it's labeled with observed distance, computational model with gravity and drag, and a computational model with gravity only. Initially, you can see that they all follow a similar path until the later portion where the computational model with gravity only begins to stray farther and farther away because it does not account for drag, as does the computational model with gravity and drag and the observed distance. Terminal velocity. Terminal velocity is when the force of drag counteracts the force of gravity, equaling a zero net force, which in terms equals a constant velocity. Terminal velocity can be predicted using a drag plus gravity model because terminal velocity is drag plus gravity. As you can see in my top right hand corner, this is my computational model with drag and gravity. As you can see, it quickly approaches a horizontal asymptote, which means a constant velocity, which in turns means terminal velocity. In the bottom right hand corner is the velocity versus time for my gravity only model. As you can see, it's linear and does not approach a horizontal asymptote, so that means it does not reach terminal velocity in this model. Is terminal force affected by an increased initial velocity? For this question, I chose to implement more code to make answering the question easier. In the while loop, I implemented an if statement. If the ball's current velocity is the same as the previous velocity in the while loop, it would print the terminal velocity of the ball and the time that the ball reached the terminal velocity. Then it would break out of the while loop. As you can see, from rest, the terminal velocity of the ball was minus 3.2998 rounding, and it reached this terminal velocity at time 5.68 rounding from rest. I went back into code and changed the ball's initial velocity to 20 meters per second in the downward direction. As you can see, the terminal velocity is basically the same as it was from rest. However, the time that it took to reach this terminal velocity is slightly different. This may or may not be due to Python's rounding error. In conclusion, the terminal velocity of an object is not affected by an increased initial velocity. However, the time may be affected. This concludes my lab.